Last class, we introduced Fourier transformations, Fourier analysis. We talked about time domains and frequency domains. We used NumPy and Python and arrays in NumPy and linear algebra in NumPy to construct a Fourier transform. In today's class, I want to look at some illustrations and some examples of Fourier transforms. We're going to spend most of our time looking at the example of the damp-driven pendulum. And we'll take the Fourier transform of data we generate with the damp-driven pendulum. We'll see that the Fourier transformation gives us a new perspective, a new viewpoint on the Fourier transform data, and we'll see the variety of frequencies that are in the Fourier transform data. In my slides, I probably won't cover it, but in my slides, I've got a couple more examples of Fourier transforms. One relates to a problem that we discussed before that arises with ordinary differential equations, and that is the gravitational interactions of the planets. It's a famous example for different frequencies in the solar system. I mean, the most obvious frequencies in the solar system are the planetary periods. 1 year for Earth, I don't know, 20 years, 50 years for Saturn and Jupiter, but there's lots of other periods in the solar system. For example, there's periods associated with the change in the eccentricity of the Earth's orbit, periods associated with the obliquativity of the Earth. And these periods you can explore and examine with Fourier transforms. Another problem that we looked at before, we talked about rabbit populations or human populations, but it also applies to the dripping tap. Those problems are described by a logistic map, and that logistic map also can be analyzed by Fourier analysis, Fourier transforms, and also contains a lot of different frequencies. Effects like the period doubling and the sequences of period doubling towards chaos, you can explore and examine with Fourier analysis. So there's a lot of reasons to explore Fourier transforms, explore Fourier analysis. I'll also mention today just a few very specific topics. I'll say a little bit about what sidebands are. I'll say a little bit about, again, what aliasing is, and what bookending. These are topics that come up with Fourier transforms and Fourier analysis. I got two slides from last class. I just wanted to remind us, is this slide here and the next slide here, because these really sort of summarize everything that we developed, the computational algorithm, the numerical method that we developed in the last class. We said that Fourier transforms were a transform from say, a time domain, time series data to a frequency domain, frequency series data. And we were representing the time domain, discrete data in the time domain as an array lowercase x, and the corresponding frequency data in a discrete frequency domain as this variable uppercase x. And we saw that a transform from the time domain to the frequency domain, or back from the frequency domain to the time domain, by these equations here that could be simply represented through linear algebra, simply calculating linear algebra and developing matrices and vectors. The frequency domain distribution is calculated from the time domain distribution by multiplied by a weighting factor and summing over the bins in the time domain. And it's really the weighting factor that picks out the contributions of the different frequencies. Think of the that weighting factor, it looks obscure. It is complex, but it's picking out the different frequencies that contributes to the frequency spectrum of the time domain data. And downstairs here, when you go from the frequency domain to the time domain, think of the weighting factor as picking out the different time bins that contribute to the frequency spectrum. So the sum is over the frequencies in the domain data, and the weighting factor is picking out the role of each time bit in that frequency spectrum. And then we wrote down these equations, which were how we were going to implement the Fourier transform for our Fourier analysis. And we saw that we could represent the time domain data and the frequency domain data as arrays or vectors in NumPy. We saw that we could represent the weighting factor that converts you from time to frequency domain or frequency to time domain as a matrix, and we could represent the Fourier transform itself from time to frequency or frequency to time as simply a linear algebra problem of a vector matrix multiplication. Okay. So that's a summary of last class, and today's class, as I say, I'm really going to focus on applying what we developed in the last class. So I think I'm going to just go to my example code, and we're going to look at the Fourier analysis of a damp-driven pendulum. And we've explored the damp-driven pendulum a lot, from just plotting the angular velocity versus time through the phase-space plot, through the Poincare section plot. Now we're going to apply a Fourier analysis to it. And the Fourier analysis brings another tool to analyze the damp-driven pendulum. It gives us another perspective, viewpoint on the damp-driven pendulum that's focused on the frequencies exhibited by the damp-driven pendulum. Okay, so here's my code. I just made my code by copying and pasting one of my earlier damp-driven pendulum codes when we were making the phase-space plots and the Poincare section plots. And in the homework, you'll just cut and paste your previous damp-driven pendulum code for this Fourier analysis of the damp-driven pendulum. Let me make this larger. So we've met the first cell several times before. It's just importing the library functions that I need for the algebra in NumPy, and also for the plotting in matplotlib. Then it's defining a couple of user functions for a numerical solution of the ordinary differential equation for our damp-driven pendulum. So I won't say any more about it. I'm using RK4, so it's an approximate solution at fourth order in the Taylor expansion, and I'm using my ordinary differential equation is representing the damp-driven pendulum with the restoring force, with the damping force, with a sinusoidal driving force. Okay. So in this cell, I'm showing you the code for defining the conditions for the pendulum, and defining the space, discrete time space, and dependent variables for the pendulum, and solving the ordinary differential equation for the pendulum exactly as we met before. So this is also just cut and paste from a previous calculation or code that I use for base plotting or for Poincaré section plotting. So upstairs here are all the parameters of the pendulum. Here, and its initial conditions. So again, just keep them simple. I've got a pendulum with a natural frequency of 1 radians per second. So it's this ridiculously long pendulum, 9.8 meters in length, that has an angular natural frequency of 1 radian per second. And then I've got the constants that characterize the damping and driving. So I've got beta the damping constant and gamma the driving constant and omega f its frequency. And I'm going to use omega f as if it's in the units of omega naught, the natural frequency, but that's 1 radians per second anyway. So here are the parameters. Right now it's set up just for a simple pendulum. So there's no damping, beta 0. There's no driving, gamma 0. And I've just displaced the pendulum slightly from the equilibrium position by a few degrees and released the pendulum from rest. So those are the initial conditions. When it comes to the plotting, we met this before. I need to define my time space, which means defining the duration over which I'm going to follow the pendulum motion and the fineness or the coarseness of the time ticks for following the pendulum motion. I define that with these two variables here. So in steps is the number of individual time ticks during the entire duration that I follow the pendulum. So I've got a large number of ticks, 20,000. And then in periods is the number of total periods of oscillation of the pendulum over which I follow the pendulum. Now, the only slight subtlety here for this if-else statement was that if I'm following a undriven pendulum, I'm going to follow it for 100 natural periods. If I'm following a driven pendulum, it's more appropriate to follow it for 100 driving periods. So that's what the if and else sets up. Then downstairs here, I'm defining my dependent variable, that's time, with the number of ticks and the range that we just specified. I'm initializing my meta variable theta that is going to dependent variable theta that's going to contain actually the theta in radians and the omega in radians per second here, and I'm setting the initial values of it. And then the very last pair of lines here is where we calculate the solution by calling our function RK4 that will solve the differential equation that's specified in the argument of the RK4 function. So I'm going to apply our RK4 function to the pendulum of the differential equation. We come out of this code with a solution of a damp-driven pendulum. In this particular case, with a undamped, undriven pendulum. Okay. So let's just jump down here to the new things that I added to this code. Once I got my solution, I do this unpacking. The solution for theta omega was wrapped up in a 2x(n) array. So I unpacked the two columns of the array into two separate one-dimensional arrays, one for theta and one for omega. So those are my solutions to my ordinary differential equation. That's upstairs here. I calculate from theta, which can extend through looping the loop in the forward direction or looping the loop in the backward direction, far off away from the origin, from zero, from the equilibrium position. I also calculate a value of theta that just tells us where we are around the clock phase. So that just runs from 0 to pi, and then back to minus pi, and back to 0 around the clock phase. So it's a theta that has extrema of plus or minus pi, and has 0 at the equilibrium position. And it doesn't reflect whether we did loop the loop clockwise, counterclockwise, or didn't loop the loop in either direction. So that's this theta here. We're then going to calculate the Fourier transform of that data, of that solution. This is new code here. I'm setting myself up with this variable and intransient to just, if I choose, calculate the Fourier transform of the data after some initial transient has elapsed. So right now, n transient set to 0. So that will cause me to calculate the Fourier transform of all of the data, all of the solution. But if I set n transient to be non-zero, then I will calculate the Fourier transform of just the steady states portion of the data. So that's the goal of introducing this variable. We've introduced it before. Jumping downstairs here, here's where I call the Fourier transform. Find the Fourier transform of the data. And I'm going to set y, uppercase y, to be the data now in frequency space rather than time space, right? In the frequency domain rather than the time domain. I do this stripping off the mirror in the Fourier transform data that we discussed a lot in the last class. So in the Fourier, in frequency space, the data is complex. That's one feature about it. It has amplitude and phase. Another feature about it is that the frequency distribution is folded or mirrored around the center of the frequency array. So there's two copies of it. And so I'm just stripping off one copy here and slicing here. We mentioned this second function last time. In addition, in SciPy, there's FFT. That's the function that will calculate the Fourier transform for your time domain data. There's an IFFT, which will calculate the time domain data based on Fourier frequency distributions. And then there's a helper function, which is FFT frequency. It's this function here, which takes two arguments and returns this array here. The two arguments are the number of data points in your time distribution. So that's the first argument. And then the second argument is the size of a tick in the time domain. And that's the variable dt. And so by calling this function, you can calculate an array where the elements of the array represent the frequencies in hertz, for example. So it's a handy way of getting a independent variable for your frequency domain data that is in hertz, and you get that array for that proxy for a independent variable in the frequency domain. You get it by this call to FFT frequency with these two arguments. So I've just done that. Okay, then we're going to plot a bunch of things, a handful of plots, And rather than walk through the text, let's just see the plots. It's smaller, not bigger. Okay, so I actually made 5 plots based on solving the ordinary differential equation, taking the Fourier transform, the solutions for the ordinary differential equation. And these plots contain both the time domain data, I'm plotting that, and also now the frequency domain data, I'm also plotting that. I also printed out a few numbers, which might be useful as reference points. These numbers up here, we had 20,000 ticks, and we had 100 periods that we recorded with that 20,000 time ticks. The natural frequency of the pendulum was 1 radian per second. So that's some information about how fast or slow the pendulum is oscillating to and fro, 1 radian per second, and how long we watch it for. We watch it for 100 swings, 100 periods, with a resolution basically determined by 20,000 ticks. So based on that, it's easy for me to calculate the range of time in seconds that we're sampling. We're sampling 100 periods. That corresponds to 2 pi times 100, 628 seconds. So we've got a duration of 628 seconds that we're sampling. The sampling frequency, given that we got 20,000 ticks over 600 or more than 600 seconds, the sampling frequency is just under 32 hertz. So every second we sample the pendulum's position about 32 times. And 32 hertz is the sampling frequency. That tells us what the Nyquist frequency is. The Nyquist frequency is the highest frequency that we can see in the time sampled data. And the Nyquist frequency is 1/2 the sampling rate. So if we've got a sampling rate that's 32 samples a second, 32 hertz, then we got a Nyquist frequency that is 16 hertz, 16 samples per second. So that will be the highest frequency we could see in the data. The interval between let me just the natural frequencies and the driving frequencies that we might be looking for. The natural frequency, on the other hand, is a much lower frequency. I wrote it out here, it's probably hard to see. It's about 1.6 hertz. So 1 radian per second is about 1.6 hertz. So the radian per second is omega. The 0.16 seconds is complete oscillations per second. 1 radian per second, 0.16 complete oscillations per second. So those are useful references. So all those numbers. Okay. So now the plots. The second plot here is just the angle of the pendulum and the angular velocity of the pendulum versus time over the 628 seconds that we were calculating. So those just show for the simple pendulum, but no damping, no driving, just sinusoidal oscillations. Upstairs here is the phase-space plot and the Poincare plot. So the green is the phase space, and the pendulum, the simple pendulum, is just circulating around this oval elliptical trajectory in phase space. The Poincare section plot is just the whole series of blue points over here that are collected on top of one another and just form this single point. And we are familiar with those. And then downstairs here are the Fourier transform of this data. This has a very simple Fourier transform because the pendulum is moving in a very simple way. It's just moving sinusoidally. This center plot, right, is the absolute value of the Fourier transform as a function of frequency. Remember, the Fourier transform is a complex quantity, so absolute value is the magnitude of that complex quantity. So it's accounting for the real and imaginary parts. Now that's the first graph here, the first frequency graph in the center here. The next one is the real component of that Fourier transform. So it could have a real part, and I've plotted the real part here. And then the bottom one is the imaginary component of the Fourier transform. If you look at those three plots of the Fourier transform of the simple pendulum data, they also almost look like there's nothing there except for this spike way down here on the left-hand side, close to the origin. This is a spike at, well, it's a spike at the natural frequency. We said the natural frequency is 1 radians per second, or 0.16 complete oscillations per second. So this is located at 0.16, and it looks to be about there. If I was to expand the scale, I think you would see that. This will just set the scale. If I remove the comment here, this sets the limits on the horizontal range for the Fourier transform plot to be 4 times the natural frequency, rather than the complete range from 0 to the Nyquist limit. So if I rerun that, you see the natural frequency of the pendulum at the settings that can be at 0.16 hertz, so 1 radians per second. And so, well, that's just a test for a discrete Fourier transform. That a discrete Fourier transform for a simple pendulum shows us the correct natural frequency of the simple pendulum. So we expected that. Let's look at a few cases of a damped pendulum. Let's add a little damping with a weak damping constant and a critical damping. That boundary between under and over damping is 1. So 0.1 is a weak damping. And let's rerun the code for weak damping. And these top 2 plots, which again in the time domain, you see the familiar features, right? If you add a damping force, we still get the oscillations with weak damping, but the oscillations will die away with a time constant set by the damping constant. So we see the oscillations die away. We see the green phase space distribution that we've met before. We see the blue trajectory of Poincare section points that we've met before. We see theta and phi versus time as the exponential, as the oscillations die off with a kind of exponential envelope. But the new stuff is the frequency. So if we look in the frequency domain, the top plot is the absolute value of the complex frequency spectrum. And then the plot below it is the real part. And the plot below that is the imaginary. we see that what was a simple spike, simple delta function in the simple pendulum, where the oscillating motion continues forever and ever and ever, becomes a broader distribution in the damped pendulum, because the oscillations don't continue forever and ever and ever. The oscillations will die off with some time constant determined by beta. We see the peak is still at about 0.16, 1 radian per second, or 0.16 hertz for complete oscillations. But you can see it's definitely much broader. We're only seeing a handful of oscillations in the time domain. Might remember that when you have damping, the damping frequency is actually not exactly the natural frequency. The damping frequency is a little less than the natural frequency. It's the square root of omega naught squared, the natural frequency, minus the damping constant squared, beta squared. So omega naught was 1, beta was 0.1. So it'd be 1 squared, square root of 1 squared, minus square root of 0.1 squared, which would be 0.01. So it is at the same level, just small, fractionally smaller than the natural frequency. So we can't really see that. But you do see clearly, right, in the frequency distribution, a big change from a short, sharp spike in the frequency distribution when you don't have damping to this much broader distribution that reflects the damping. If we were to increase the value of beta, let's go to 0.2, then we'll have an even smaller number of oscillations, but they're over in a smaller period of time. And if you can remember the previous plot, this seems to be a broader distribution now. As we increase the damping, we get a shorter and shorter view of the oscillations. We get a broader and broader distribution in frequency space. If I go to 0.5, you'll really see this. You know, with 0.5, we have a couple of oscillations. We've got a very broad frequency distribution that you can now see is not peaked at the natural frequency, but it's peaked at some value below the natural frequency. That value below the natural frequency is now, we said, the square root of omega naught squared minus beta squared. So now it's the square root of 1 squared minus 0.5 squared. So that's going to be 1 minus 0.25, so 0.075. And so you can see that this peak is moving, it's visibly moving down. And the whole distribution is much broader. So that would be how to recognize effects of damping in pendulum motion in the frequency spectrum. It's very clear in the frequency spectrum. Let's go back up here and put on a driving force. I think I did my calculations for 0.25 for the value of the damping constant when I have a driving constant. And I need to have damping and driving to avoid this problem of just infuse. You have no damping, you're going to be infusing energy all the time. The oscillations are going to be getting larger all the time. We want to see a steady state, have a balance of energy infusion and energy dissipation with damping and driving. Okay, so beta is 0.25, and then I'm going to walk through a bunch of values of gamma. So this is gamma 0.1. So gamma at point one is what we would call weak driving, like we called the beta at point one weak damping. For the damping, it was a beta that was small compared to the critical value. For the driving, a weak gamma of 0.1 is small compared, means that the driving force is small compared to the gravitation. So we release the pendulum. There's some transient period of more complicated motion that depends both on the natural period of the pendulum and the driving period acting on the pendulum. But after that transient period, you reach a steady state where the pendulum's motion just depends on the amplitude and the frequency of the driving force. That's what's controlling the pendulum. And so you see that probably most clearly in the Poincaré section, phase plot, right? In the phase plot, the initial transient is this sort of unusual curve. It starts at this location here, the initial coordinates of the pendulum. But after some period of time, after the transient, you're basically going around this inner oval here. The pendulum just orbits around and around and around that inner oval. And you can see this because these are many Poincaré points located at essentially the same position on that steady state trajectory. You can also see that you're not steady state for these first few oscillations here on the left, but you're certainly steady state for the oscillations over here on the right. So what's the Fourier transform look like? It looks like these three plots here. This is the absolute value, this is the real part, this is the complex part. It looks like a single frequency. Now this is the Fourier transform. Let me actually redo this. Let me put on a transient tab. It's not so much important here with weak damping, but it'll help us with the strong damping cases. So I put on a transient card. That because I did that, the transient is highlighted in red here. Green is the steady state. But what we see when we're in steady state is this essentially single frequency of in the motion of the pendulum, and that's the driving frequency or the driving period in the motion of the pendulum. My driving frequency was 2/3 of the natural frequency of the pendulum. The natural frequency of the pendulum was 1 radian per second, or 0.16 hertz. The driving frequency then is 2/3 of radian per second, about 0.11 hertz. And that's this location. So we're just seeing the driving period, and we're seeing the pendulum oscillate with a relatively small amplitude. Right? The oscillations are sort of 1/10 of a radian, roughly inside. Okay, let's go and turn up the driving constant. This is what we're going to walk through as we walked through before to approach bifurcation and chaos. Okay. So now we jumped up to 0.9 for the driving constant. That's the world of strong driving. That driving force is the same scale as the gravitational force on the pendulum. We still see that there's some transient motion that's complicated. upstairs here in red, and at early times on the left in the second plot. We still see at later times we reach a steady state with oscillations around this green oval upstairs, and what look like periodic oscillations over towards the right on this plot here. If we were to look more carefully on this plot, it's a little hard to see the scale of this plot, but the oscillations are still periodic with this large damping compared to the small damping. But unlike the small oscillations, driving, where the oscillations were sinusoidal, now these oscillations are not exactly sinusoidal. They're still periodic, but they're not sinusoidal. Well, what does a function, supposing we've got a repetitive oscillation, but it's not simple sinusoidal oscillation. An example we met before was a square wave, sawtooth, right? What we saw was that the square wave and sawtooth are periodic. They're not sinusoidal. They have a lowest harmonic, which corresponds to the period of the square wave of the sawtooth, but they also have higher harmonics that determine the particular shape of the square wave or the sawtooth. And that's what you're seeing here. For example, at this point here, we've distorted a little bit the sinusoidal oscillations to be just periodic oscillations. And you can see that in addition to the lowest harmonic, there's a contribution from this frequency here, which means that the shape is no longer simply sinusoidal. It's still repetitive, periodic, but it's not sinusoidal. Let's increase the. So it's a useful way of getting an understanding, getting a picture of the repetitive but non-sinusoidal motion of the pendulum with the Fourier analysis. Let's go up again in strength. We'll go to 1.05. So, 10 or 15% larger. This brought in an interesting effect when we used this value before, because we looped the loop. The pendulum looped the loop during that transient period. And so we moved away from sort of oscillating about no complete oscillations to a steady state oscillation about the point where you have completed a fixed number of oscillations. Way over here, so four complete oscillations. Anyway, so this is the base phase concurrent section plots again. You see the looping the loop here in theta and omega versus time. You see the looping the loop in where we're at steady state in green, oscillating around. Let's take a look at the Fourier transform here. After waiting out the transient period and the complicated motion in which we loop the loop, we get a steady state period, which is determined by the driving frequency and driving amplitude of the pendulum. And we see a large peak at the driving frequency of the pendulum. It is a repetitive motion, but we also see in greater intensity, higher harmonics for the steady state region of the pendulum. You can actually here, double the frequency. There's again one here, triple the frequency. I can see it because I'm close to the pixels. I don't know if you can see there's also a contribution here. And 4 times the frequency. And so that describes the shape of this oval in phase space. So again, it's a useful way of analyzing the data to see how the frequency components, the harmonics, are changing. 1.07. Just 2% larger driving force from 1.05 to 1.07. So, face space and Poincaré section plot look similar but not the same. Right? They both show the looping the loop. This one for 1.07 and the previous one for 1.05. They both show a steady state at large times. In green is the phase-space trajectory at large times, which was some sort of oval with gamma equals 1.05 and one similar oval gamma equals 1.07. But if you were to look in detail, there's two ovals here, the inner and outer one. There's two Poincaré section points, one to the left and one to the right. One complete period now corresponds to going around the oval, outer and inner oval, going through both the left and the right Poincaré section points. So this is period doubling. We see the period doubling in the frequency distribution also. So like before, we see the driving frequency. That was at 0.11. And we also see multiples, harmonics of the driving frequency. Like here's 0.22. Here's 0.33. But we see other frequencies too. Now, remember the harmonics, when you have repetitive but non-sinusoidal oscillations, the harmonics are always multiples of the natural frequency or the driving frequency. They're always higher frequencies. They're always integer multiples of that driving frequency. But now we see frequencies that are at lower frequencies. This is the effect of the period doubling. We got a peak at the driving frequency, but we got a frequency in the data that is half the driving frequency. So we can see very clearly in the Fourier analysis in the frequency domain the effect of the bifurcation, the period doubling, which shows up very clearly. Let's 1.079. So now we're just incrementing the, I got this dial, right? I'm turning the driving constant gamma up. Now I'm just turning it up by less than a percent. So a very fine adjustment of the driving constant. What we see here is that we've actually incurred an additional period doubling. So remember we were going around two loops in the phase space plot. Now one of those loops was period doubled into a pair of loops. So we actually have effectively three loops in the phase space plot. We can see that perhaps most clearly with the 3 points in the phase Poincaré section plot. Remember, the Poincaré section plot is like looking at the phase space trajectory stroboscopically, probing your location in the phase space plot once every driving period. You're finding that there are 3 distinct locations during the steady state that you can be in during the driving period, indicating that it's going to take you 3 times as long based on one period doubling and then another period doubling to complete one complete oscillation. That oscillation is what's repeating. You see it extremely clearly in the frequency distribution down here. So again, we see the driving frequency, that's at 0.11. We see harmonics of the driving frequency. This is 0.33, so this is a harmonic of the driving frequency. I think this one is too. It's a harmonic of the driving frequency. But we see other frequencies too. We see a much lower frequency, 1/3 the driving frequency. So this is the period doubling plus another period doubling gave us a period that's 3 times the driving period. So that's this piece here. So that's at about 0.35, 0.035 hertz. And you see harmonics of it too. It too is not periodic, it's periodic, but it's not sinusoidal. So we expect to see harmonics of it. And so I think we can't associate, for example, this peak here as a harmonic of 0.11 hertz, but it is a harmonic of this 0.0, whatever it was, 1/3 of 0.16.
Yeah, I don't see it like a spike of 0.22.
The 0.22. Yeah, so the amplitude of the higher harmonics depends on the detailed shape of the trajectory in phase space, right?
Yeah.
You know, like, is it like a square wave? I don't know. But if it would be a square wave, it had a certain thing. If it was a sawtooth, it had a certain pattern of harmonics. So somehow not seeing a harmonic or seeing a large harmonic is reflecting the exact trajectory in phase space. But I don't know, I don't have an intuition as to whether we would expect to see a large second harmonic or third harmonic. But yeah, it's telling us a lot of very useful information. Anyway, so we've seen that from the Fourier analysis. I think what we've reached the point of doing is incrementally, when we looked at the damp-driven pendulum a lot, and we've looked at it a lot to introduce a lot of different ways of looking at data. We've introduced the phase space, we've introduced the Poincare sections, we've introduced the Fourier analysis. We've always been looking at the damp-driven pendulum, but all of those tools are applicable to all sorts of problems. I mentioned the harmonics of the solar system. In the solar system, you can see periods from, you know, Earth's yearly periods, Saturn and Jupiter's 20, 50-year periods, to periods like the period of the oscillation of the eccentricity of the Earth's orbit, I think is like 100,000 years. And it has 2 components, 100 and 400,000 years. So if you were doing a calculation, solving an ordinary differential equation for the solar system and the gravitational interaction, you could analyze the data and you would see the ellipse varying on timescales of 100 and 400,000 years. You also see the Earth's axis. It's obliquity. I'm saying that wrong. You know, it's at like 24 or 23 degrees, and that causes, you know, the seasons, the summer and the winter. But that changes over time, and that has a period, I think, of 40,000 years. And all this arises because of the gravitational interaction. Saturn and Earth and Jupiter actually create the stretching and compression of the Earth's eccentricity, its orbit. And the sun and the moon actually create the tilt of the Earth, the fact that it moves backwards and forwards. And you can get all of that out of solving the ordinary differential equation for the many-body gravitational problem of just got to put in the sun, you've got to put in the Earth, you've got to put in the moon, you've got to put in Saturn and Jupiter, and you get all these features, all these frequencies that are inside the solar system. Yes.
I'm just wondering, so what point in your code did you impose that we're skipping past the transient period?
I applied it.
Because I'm trying to, like, I'm getting that, and I feel like to get your time array to be the same dimension, you have to skip over some frequency value.
Yeah. So I could find my basically a cut on what I was going to call transient versus steady state. 10,000, right? When I do the Fourier transform of the data, I only transform the steady state. I slice it in.
Okay, so it's when you
So,
have to do it.
yeah, so I call the Fourier transform not with the entire array of data, but with a sliced array of data. So that gives me the Fourier transform in just the steady state region. So that's all I had to do that. And I think that's pretty much all I did. When I calculated the number of points here, I also said that I just want the number of points that I'm doing the Fourier transform of, that I'm Fouriering and analyzing the data with. So I applied the transient cut there too. Okay. I'll show you one more. We went so we've seen a couple of bifurcations there. We could try and follow the bifurcations. They get increasingly closely spaced, so increasingly difficult to follow. But if we were to increase gamma by another 10%, this is gamma of 1.19, we have moved from the region of bifurcation and sort of steady state motion to beyond bifurcation in chaotic motion. So these are the phase space plots, and theta and omega for gamma of 1.19, right? And at 1.19, the motion is chaotic. In green, right, this is the transient, this is the steady state, supposedly the steady state region. We no longer have the steady state region. These are the three Fourier transforms. Really, this is the Fourier transform. This is the absolute part, the real part, the imaginary part. They look very noisy. They're not just random noise. So this is the point about chaotic motion. Chaotic motion is not like random motion. You know, if you know the pendulum's position at one moment in time while it's undergoing chaotic motion, you can calculate it at the next moment in time. You can calculate it accurately. So it's deterministic. It's not like random motion. So chaotic motion is different from random motion. In the Fourier transform, you see kind of noise, a randomish noise, but it's not completely random. For example, you see still in the Fourier transform, when you've got chaotic motion, you see the driving frequency and its harmonics are still in the Fourier transform, because the driving frequency is still pushing or pulling on the pendulum, right? So the driving is still there. You see the driving effects in the pendulum motion. If I was to expand the scale, let's just go back up. So we were looking at a reduced scale to see the natural frequency and see the driving frequency, but go back to the full range. So this is from 0 to the Nyquist limit. So to a much higher frequency. The natural frequency and driving frequencies are way down here on the far left. You see that in chaotic motion, you've got a noisy Fourier distribution, a noisy frequency spectrum across the entire frequency. Now, random motion would correspond to a completely flat Fourier distribution, frequency distribution. That would be random motion. This is not random motion, and it's not completely flat, right? It's noisier over here on the left at low frequencies. The noise dies off over here on the right at high frequencies. So again, chaotic motion is not random motion. The frequency distribution of chaotic motion and random motion are different. The frequency distribution of random motion is just a, if you look in frequency domain, you would see just a uniform frequency distribution for random motion. But for chaotic motion, it's different. The frequency spectrum is noisy, but it has a distribution where there's more larger amplitudes of the frequencies at low frequencies than there are at the higher frequencies. And you see the driving frequency and its hormones. Okay. Let me show you. This is now got 3 little codes, just to show you 3 little features of Fourier transforms that often come up in Fourier transforms. So you might just recognize them in Fourier transforms. So I'm going to go back to my directory here. Sidebands. I just want to show you, sideband is a term that gets thrown around with frequency distributions. And let me show you what a sideband is. What does that mean? In this code and the next code I'll show you, I'm just generating two sine waves. And I'm going to combine those 2 sine waves in this code in different ways of combining them, adding them, multiplying, so I can show you sidebands. So signal number 1 and signal number 2, these parameters define the 2 signals that I'm going to combine in this example for sidebands. To be concrete here, what I'm imagining is that I'm going to record the duration of these combined signals for 1,000 seconds at 1 hertz. So I'm going to have 1,000 samples separated by 1 second between ticks. So I'm just going to define that here. The first signal has a frequency of 0.1 hertz. So it has a period of 10 ticks. And the second one, it has a frequency of 0.01. So that's a period of 100 ticks. So I've got a low and a high frequency signal. I then would, those 2 signals, the high frequency, the low frequency signal, I'm going to combine them in several different ways. And then I'm going to calculate the Fourier transforms of those combinations. So here's my dependent variable. This is time. This is the 1,000 ticks over 100 seconds. We've done that a lot. Here are my 3 different combinations of the amplitude A0 corresponding to the first signal and amplitude A1 corresponding to the second signal. In Y1, I just add the 2 signals together. So I've got a low frequency sine wave, we've got a high frequency sine wave, I've got the sum of the low and the high frequency sine wave. In Y2, I just multiply those 2 frequencies together. I've got the low frequency sine wave times multiplying the high frequency sine wave. And in item 3, I've just made a more complicated combination of the 2 sine waves that involves both multiplying and adding. So I've got, in this term here, I've got a product of the sine waves. from this piece with A0 times this piece with A1, but I've also got just A0 on its own. And then I take the compute the three Fourier transforms, the three different sine waves, the three different combinations of the sine. So we get these uppercase y's, which are the frequency spectra of the three different superpositions of sine waves. Let's look at those. Let's run this whole thing. Okay, so after I've made the calculated the Fourier transforms, I'm just going to plot the time domain for the three signals and the frequency domain for the three signals. I won't show you the plotting code, it's snappy. But I want to show you the results. This one on the left upstairs is the sum of the two sine waves, the low frequency one and the high frequency one. The high frequency period you see is 10 samples, and the low frequency period is 100 samples. I'm just plotting the section of the full time duration that we sampled this data. So that's the sum. This is the product. This product here is the low frequency times the high frequency. So I think in this you can see how the low frequency multiplying the high frequency is kind of modulating the high frequency. You see the high frequency, but it has an envelope that is the low frequency. So again, you see the low frequency and the high frequency here. And then this is this combination where I've got both of the effects of adding together signals and multiplying signals. And that's just an example I'm going to mention when I talk about the Fourier transforms. So when we added them, what does the Fourier transform look like? If you just add two sine waves together, in the Fourier transform, you're just going to see those two sine waves. So that's what we see here. These two peaks. When you multiply them, what do you see? What you see is what we would call sidebands. And most clearly here, but these two frequencies here when we multiply the two sine waves together, they're not the high frequency. They're not the low frequency. They're the high frequency plus the low frequency, high frequency minus the low frequency. So that's why we call them sidebands. It's like omega 0 plus and minus omega 1 are the two sidebands. And so that's what you're seeing in this data here. In this case here, where I've taken the high frequency and I've multiplied it by 1 plus the low frequency, I see the high frequency. And we see, in addition, from the product of the low and the high frequency, we see the sidebands here. And I made this one because think about, fashion now, but radio waves, TV antenna, TV waves. Those were carried by a combination of a carrier frequency that's a high frequency, on top of which you apply a messenger frequency that's the low frequency. So that funny combination of the low frequency and the high frequency that I made, that is effectively the high frequency is the carrier frequency. It's going to be the carrier for the low frequency, the messenger frequency. And that's how we would, 100 years ago, whenever, transmitting radio waves and TV waves through the air by carrying the message on the back of a carrier frequency. And so here you see the carrier frequency, this sharp spike in the centimeter, and the information, the message is carried on the sidebands, the sideband frequencies. So that's what sidebands are. And they come up a lot at engineering, physics, all sorts of places. I'll show you one more. Just wanted to show you aliasing. Same business here as the last little notebook. I'm going to define some discrete space of time, region of time, 1,000 ticks over 1,000 seconds, so 1 tick a second, 1 hertz sample. I'm going to define 2 frequencies. Now these are, remember the frequencies in the last example were much lower frequencies than the sampling rate, 0.1, 0.01. These 2 frequencies here are one's 0.4 hertz, one's 0.6 hertz. This Nyquist limit is 0.5 hertz if you sample at 1 hertz. So the 0.4 is observable in the data, it's just below the Nyquist limit. The 0.6 is not observable directly in the data, it's above the Nyquist limit. So I'm going to take these 2 frequencies and I'm going to find the Fourier transforms of these 2 frequency distributions when they're sampled at 1 hertz, when one of them is above, one of them is below the Nyquist limit. We'll see what the Fourier transforms look like. And so that's what I do downstairs here, right? Here's my independent variable, but here's my Y1 is my lower frequency below the Nyquist limit. Y2 is above the Nyquist limit, the higher frequency. Here I take the Fourier transforms to get uppercase Y1, uppercase Y2, that are the frequency domain versions of these signals. Okay, so let's just quickly run this. And then I obviously plot them. Here's the plot. Same plots as before, but on the left-hand side is the time domains. These are really high frequencies, 0.4, 0.6 of a hertz. And so this just looks like a blue square, but it's very rapidly oscillating high frequency. One above, one below the Nyquist limit. I take the frequency, I Fourier analyze both data, the high and the low frequency. I get these Fourier distributions. These are frequency distributions. They look exactly the same. The time distributions were very different. One was a 0.6 hertz, the other was 0.4 hertz sinusoidal signal that I digitized or sampled at 1 hertz. But when I take the frequency distribution, I see the same frequency distributions. What's going on here? Well, in the top plot, this was the lower frequency. This was the true frequency was 0.4 hertz because it's below the Nyquist limit. I see it at 0.4 hertz. The bottom sheet, that was the high frequency. It was 0.6 hertz. It's above the Nyquist limit. I can't see it. What frequency do I get? I had mentioned an equation for what we call the alias frequency. The alias frequency is the sampling frequency. Sampling frequency less the true frequency. The sampling frequency is 1 hertz. The true frequency is 0.6 hertz. 1 minus 0.6 is 0.4. This is the alias frequency for the 0.6 hertz that's above the Nyquist limit. So this is just a warning that there is a limit on what frequencies you can see in a Fourier transform, the Nyquist limit. If you have frequencies in your data that are above that limit, they don't just disappear off the map. they get unfolded into lower frequency. And we're seeing that lower frequency here. We can't actually distinguish between the 0.4 hertz signal in our data frequency spectrum, either being the true frequency or the or an alias higher frequency.